Hello everyone. In this session, we will have a look at a few of the spatial square matrices. The motive here is to reduce the space requirement of these matrices. After these, we will look at sparse matrix too, along with some common operations on them. By square matrix, we mean there are equal number of rows and columns. A few of the spatial matrices we are going to cover are diagonal matrix, tridiagonal matrix, lower triangular matrix, upper triangular matrix, and symmetric matrix. Here we have also listed the unique property of these matrices. A diagonal matrix is one that has all zero elements except the diagonal entries, and diagonal entries are identified by same row and same column index, that is 0, 0, 1, 1, 2, 2, and so on. Tridiagonal matrix is the one which does not have an element if the difference between row and column index is greater than 1. That is, in such a case, the entry is 0. Then we have lower and upper triangular matrix, which respectively contain values in the lower and upper half of the matrix. If I is representing the row index and j is representing the column index, then for lower triangular matrix, if I, that is row index, is greater than equal to the column index, then entry is 0. Similarly, if row index I is less than equals to the column index j, then in case of upper triangular matrix, the corresponding entry is 0. Lastly, in case of symmetric matrix, the entry pairs I, j and j, I will have same value. By knowing these properties, one may try to efficiently store these matrices in linear space complexity instead of the complexity of order of n square. As to store a two-dimensional matrix which is a square matrix, then we have to declare an array of size n cross n. Hence the complexity, it comes out to be n square. But here we will try to reduce this n squared complexity to linear space complexity. By doing this modification, one has to also work on the operations of retrieval as well as storage to have better time complexity too. Starting with a diagonal matrix, normally we will use a two-dimensional array for this square matrix, but after knowing the fact that it is a diagonal matrix, we can store it using a one-dimensional array containing only the non-zero matrix entries. For example, in this diagonal matrix, we just have to store 4 non-zero diagonal entries, that is 2, 1, 4 and 6 in one-dimensional array as is shown here. However, when we retrieve the elements of this diagonal matrix, then an element will be printed only if row number equals to the column number, else 0 will be printed. Similarly, talking about tridiagonal matrix, then in addition to the main diagonal, elements will be present in two more diagonals, one below the main diagonal and one above the main diagonal. These are identified with these two conditions: row number equals to column number plus 1 and row number equals to column number -1. In such a matrix, there will only be 3n-2 non-zero elements. So, instead of declaring a two-dimensional array, we will declare a one-dimensional array of size 3n-2. Now, the point is how to take input from the user. So, there can be three possibilities. We can take the input row-wise or column-wise or diagonal-wise. Here we have taken input row-wise, so the contents of one-dimensional matrix will be 2, 1, 3, 1, 3, 5, 2, 7, 9 and 0. Again, while retrieval, we have to take care of the three conditions which are specified at line number 11. If these conditions are satisfied, element will be printed, else we have to print 0. Now, looking at triangular matrix, then elements are present either in the upper triangular or lower triangular region. Also, total number of non-zero elements comes out to be a summation of a series from 1 to n, which equates to n into n plus 1 by 2. There can be two ways to take the input here, either row-wise or column-wise. Row major order for both the upper and lower triangular matrices shown here comes out to be same. However, the column major form will differ in both the cases, and the same is shown here. Again, we proceed with row major order. So, the contents of one-dimensional array are 2, 5, 1, 0, 3, 1, 4, 2, 7 and 0. Now, to retrieve upper triangular matrix, the condition to be checked for non-zero entry is row index is less than or equals to the column index, and that for lower triangular matrix, the condition gets changed to row index is greater than or equals to the column index. As far as symmetric matrix is concerned, then one can store either the upper half or the lower half, that is either the upper triangular or the lower triangular matrix as we have done just now. Then some mapping can be derived to retrieve all the elements of the symmetric matrix. After these spatial matrices, we have to look at the sparse matrix and a few of the operations on it. A sparse matrix is one which has a few number of non-zero elements, but they do not follow any pattern. For example, the matrix shown here has only 5 non-zero elements out of 16 possible entries. So, it's a sparse matrix and there is no relation with respect to the positions of these 5 elements. The two popular ways to store such matrix are using arrays and using linked list. Here we will look at the array representation of sparse matrix, which is also known as triplet. The triplet is represented using a two-dimensional matrix which has 3 columns and number of rows will be equals to the number of elements in the sparse matrix plus 1. So, in this example of sparse matrix, we have 3 columns and 9 rows as there are 8 non-zero elements in the given example. The first row will have dimensions of the sparse matrix, number of rows are stored in the first column and number of columns are stored in the second column, and the third column will have total number of non-zero elements in the sparse matrix, which here is equals to 8. So we have 8 present at the 0th row and second column. Next, we have to scan the sparse matrix either row-wise or column-wise, and we have to note the row index, the column index, and the value of the non-zero element. So here we will scan row-wise. The first non-zero element 15 occurs at index position 0, 0. Then 22 is present at index 0, 3. Then minus 15 at 0, 5. 11 at 1, 1. 3 at 1, 2. Minus 6 at 2, 3. 91 at 4, 0, and the last element 28 is present at index position 5, 2. So, in this way, we can store large sparse matrix that will save a lot of space in case of big dimensions. After storing the sparse matrix like this, next we have to perform operations on it. We are going to look at 3 operations: transpose, addition, and multiplication. To compute transpose, one has to simply interchange the rows and columns values. Here we have just computed this triplet for the matrix. To get the transpose, just interchange the values under column heads row and COL. The third column will remain as it is. The triplet thus obtained will show the contents of transposed matrix in column major order, and we are working in row major order, so we just have to arrange the rows except the first one in non-increasing order of the first column titled row to get the final triplet from this column major representation. So here is the rearranged triplet and it is in the row major order now. The sparse matrix corresponding to the obtained triplet will be like this, and it is the required transpose of this matrix also. Now, in order to add two matrices, we have to look at elements which are lying at same index positions. For example, here we have values in both the matrices at index position 0, 0. So, the resultant matrix will have 3, 0, 30 at this position, that is 0, 0. Also, we have to first verify for the same dimensions of both the matrices before proceeding. Since we are working with triplet representation of sparse matrix, so we will have these matrices in this form as is shown on the screen right now. Here, there is no problem with the dimensions. So, the dimension of final matrix will be 6 cross 6 only. However, we are not sure about the total number of non-zero elements into the final added matrix. So, a counter can be maintained for the same. Here we have initialized this counter value to 0. Now, we will look at the row-column pair in both the matrices. If they match, the corresponding elements have to be added, else the value will be copied from either of the two matrices as it is into the resultant matrix. Here, 0, 0 is a match. So, at index position 0, 0, values will be added and we get 3, 0, 30. And also, we have increased the counter by 1. Now we have 0, 3 entry as we have to follow lexicographic order. There is no match for this entry, hence it will be copied as it is into the resultant matrix. Also, the counter is increased by 1 again. In this way, one has to scan all the entries in order to get the final triplet after addition. So, one can complete the scanning like this. Lastly, the value of the counter will be used to fill the value at index 0, 2, which in this case comes out to be 14. Lastly, we have to look at multiplication. So, if we have to compute A cross B, then first take transpose of matrix B, that is the second matrix, and then multiply the corresponding elements and take their summation for each position in the resultant matrix. Normally, when we have to multiply two matrices, then we follow this procedure. Each row of matrix 1 is computed with each column of the second matrix by multiplying the corresponding elements followed by their summation as is shown here. First row with first column, then first row with second column, third column and fourth column. Now the same process is repeated with other rows of first matrix to get the final matrix. This is what we normally do, but here we will first take the transpose of matrix B. So now to get the final answer, the rows of first matrix as well as second matrix will be considered one by one as is shown here. First row elements of first matrix will be considered for each of the rows of the second matrix. Then the process is repeated with other rows of first matrix to get the final answer. We are working with triplets. So here we have the required representation of both the matrices we are working with in the previous slide. Then we have to take the transpose of second matrix. Now we have to compute row wise. So row 0 of first matrix is processed with row 0 of second matrix, and wherever we have same column we have to multiply, then add. So here we have two values in first matrix and single value in the second matrix, and we have same column 3, 0, 3, 0, 3. So 12 and 20 will be multiplied and the corresponding index of the resultant matrix will be row indices of both the matrices. So here we have index 0, 0, and the value it comes out to be 12 into 20, that is 240. Again, here we are not sure about the total number of entries in the resultant matrix, so a counter is maintained and now we have increased its value by 1. Next, 0th row of the first matrix is processed with the first row. So we are talking about the index 0, 1. 0th row of first matrix and first row of second matrix. And here again we have same column, that is 3. And here in the second matrix we have same column number 3. So we have to again multiply 12 and 25. So the value corresponding to index 0, 1 comes out to be 12 into 25, that is 300. Next entry is 0, 2. But here there is no common column. So no entry will be there in the resultant matrix. Lastly, for index 0, 3, we have a common column 1. So for 0, 3, we have to multiply 10 and 23. Hence, the corresponding value for index 03 comes out to be 230. Now the process is repeated for other rows also. For second row of the first matrix, we have single entry at column 2. And also in second matrix, we have only one entry in second column corresponding to second row. So basically it's a match. Thus at index position 2, 2, value comes out to be 45. That is 5 cross 9. Then for third row of first matrix, we have entries for columns 0 and 1 only. So here in second matrix, we have columns 0 and 1 only with rows 2 and 3. So for index 3, 2, the common column comes out to be 0 and hence the corresponding entry will be 15 cross 8, that is 120. Lastly, for index 3, 3, we have common column 1. So value comes out to be 12 into 23, that is 276. With this, we have completed the process of multiplication also for the given two matrices, and the corresponding sparse matrix obtained is also shown here. So in this way, one can store the sparse matrix with the help of triplet representation and can perform the required operations. That's it for today. Thank you.